Okay, so in this problem, I have a shell and tube heat exchanger. So the condition here is that it is a shell and tube, and then it is a 4/8 shell tube pass. So there are four shells, and then each has an 8 tube pass for this process. And then the cooling fluid is also water with a flow of 5 kilograms per second. So siya yung pumapasok sa shell side, and then water din yung ating hot fluid that flows on the tube side of our heat exchanger. So it says here also that the overall heat transfer coefficient is at 800 watts per meter squared degrees Celsius. We need to calculate the area or the total area of the heat exchanger as assuming all four shells have the same size. So let's write muna yung ating mga initial mga given natin. So we have the inlet fluid. So we have there the 5 kilograms per second water, and then this to be cooled from 90 degrees Celsius going on the outside, so that's 70 degrees Celsius. And then the tube heat exchanger having 4 shell passes. So the other fluid, so this is the hot fluid, and then the other fluid, which is the cold one, is also 5 kilograms per second, and it enters at a temperature of 50 degrees Celsius. So of course, the outside temperature is not given, so we still need to find this one. And kung mapapansin nyo, hindi ko na-specify kung ito ba is countercurrent or co-current, because in shell and tube, sometimes nagkaka-interchange sila. But the way that we can determine the movement of that arrangement is to look at the Paris Handbook at section 10. Okay, so here is a table at figure 11-4, graphs. So mapansin nyo dito, you can read something at the footnote. That's the LMTD, or the correction factors for heat exchangers. And then there's a lot of combinations right there. Merong 1 shell pass, 2 or more tube shell passes, and then 4 shell pass. So in our problem, we have 4 shell pass, and then 8 multi-tube passes. So in this case, we have letter D for that. So that's letter D, and it's right here. So dito sa Paris Handbook, kung mapansin nyo, medyo iba yung designation niya. The letter T, that is small letter, they are the cold fluid, and then this capital T are the hot fluid. So basically, in this case, kung mapansin nyo, yung inlet ng cold natin is kasama ng ating outlet na colder fluid. So, yes, that's correct. So in the Paris Handbook, you can see here, the capital T here represents the hotter fluid, and then the small t actually represents the lower temperature or the colder fluid. So in this case, we can still say that the movement or the flow is still countercurrent, because if you can see right through here, the inlet comes or the hot fluid comes on this portion here, and then the fluid comes out right through here. That's a countercurrent flow of our fluid, and then it goes out right through this T2. So we can also say that we'll be using here the countercurrent. But of course, even though this is a countercurrent flow, Ft is not equal to 0, because we're using the shell and tube, and knowing that this shell and tube would give us this yung portion bago mag second or third shells would give us a different movement of our flow. So hindi strictly siya countercurrent. So with that, we know that Ft is not equal to 0. And then we can also determine Ft using the formula for our RNS. So R is actually, based on your handout, we could say that R is the capacity ratio and effectiveness is S. So R is simply the hot fluid temperature change, that's our THI, and then THO, and then the cold fluid temperature change. And then S is the minimum heat capacity fluid temperature rise, and basically it comes from our colder fluid, and then the difference in the temperature would be that from the hot and then the colder fluid. So I'll just be copying this so that you won't forget these definitions. And then I'll paste it right here so that we know how this thing works. But to find this FT, we need RNS because based on this expression, the ratio of the RNS or the values of the RNS will give us this FT. But to do that, we need actually to determine all the temperature profiles that we have. But kung mapansin nyo, kulang tayo ng TCO. So before anything else, before we can find FT or any ratio for this effectiveness or capacity ratio, we need to find TCO first. And to do that, we will be deriving or we will be using our energy balance sa heat exchanger na to. So basically, yun lang naman ating heat exchanger is nag-balance lang yung ating heat between these two fluids, diba? Sabi natin, yung Q in is just equal to Q out. So basically, kung ano yung nilet out ng ating hotter fluid dito, yun yung tinake in lang ng ating colder fluid, which is the same. Water lang din sila, no? So basically, that's just giving yung ating sensible heat kasi wala naman nagkaroon ng ating wala naman nagkaroon ng change of phase. So we can just do this this is the hot fluid and then this is the cold fluid. So that's MCP delta T. And we know very well that for our hot fluid, we have 5 kilograms per second, and that's for the hot fluid. And then the specific heat capacity is obtained in between the average temperature of 90 and 70. So the average specific heat capacity, I've already pre-computed for that. So that's 4,200. So that's 4,000. That's 4,200, and then that's joule. 0.6342. That's joule per kilogram Kelvin. And then the change in temperature is actually equal to 90 minus 70. So this is the value of our Q. And basically, if we have this value of Q, that is simply equal to, of course, the mass flow rate of our colder fluid, and then the average specific heat capacity, and then the temperature difference, which would give us the TCO minus 70 degrees Celsius right here. 50 pala. So we have TCO minus 50. And then, of course, yung CP natin dito is a function of our TCO, and then the CP is a function of TCO, and then yung ating TCI. So, we still need to find this specific capacity na dependent naman din sa TCO. So, hindi siya ganun kasimple kasi nga, CP is dependent on the average of this one. So, how do we get that if we don't actually have the value of the temperature? So, instead of using the thermodynamic properties, because yun nga yung nagbibigay sa atin ng specific capacity, that is very applicable kung meron kayong dalawang temperatures given. But if not, then we need to find another expression for our CP that would give us the equivalent of that using temperatures. And in this case, we can check on the specific heat capacity of pure compounds on table 2, section 2, and you can see here the heat capacities of organic liquids. So you can check on 2-165, but I am using the 8th edition. So you can check here the organic fluid, which is water, and eto siya dito sa number 342. So it says here that we have this kind of values right here. So it says here we have 7732. So yan yung mga values natin. Then yun yung cast number ng ating water, and ang mahalaga dyan is itong C1 to C5. And then yung ating gagamitin na equation, which is this one. So itong number 1 yung ating gagamitin dito kasi based on our expression, based on this table, so yun daw yung ating gagamitin. So let's take a picture of this para ilipat natin siya sa ating solving pane. Yung C5 lang naman yung importante dito. So let's just check on C. Ito yon. Okay, so we have here for water, and then the formula right here is this one. Okay, so now that nalagay na natin yung ating mga necessary values, we should also take note that the CP that we'll be obtaining from right here is in joule per kilomole Kelvin. So, of course, that's given ang ating mga values are consistent with this. So, if we have obtained CPL, we can also convert that to a certain value, which is in kilograms. So, in this case, let's try to substitute and find CPL using our temperature. And since we need to convert this Kelvin, in Kelvin, we need to convert this temperature right here. Pero dito sa portion na to, there's no need naman na galawin pa natin to kasi kung mapansin nyo, na-solve na naman natin siya before. So with this, let's convert this to Kelvin. So we have 50 plus 73.15 is 323.15. So this becomes 323.15 Kelvin. Okay? So with this, yung expression na to, in terms of our average specific heat capacity for water, so we have Cp of L is actually equal to C1. So C1 is, we have C1, C2, and then C3, that's C4, and then we have C5 for this particular equation. And then our specific capacity of liquid is based on this expression, we have C1, so that's 276.370, and then we add this C2 at the temperature of the average temperature, so we get minus 2090.1 times the average temperature, which is our TCO, plus 323.15 Kelvin divided by 2. Okay, and then we add this with C3 T2 T squared, so we have C3, that's 8.125, and then again the average, and then we add C4, so that's negative 0.014116, and then this is T1 TCO plus 323.15 divided by 2, and then that's cubed. Okay, and then the last one would be C5 versus T4. Actually, this is one of the typographical errors of Paris Handbook. So, kung di nyo alam, ito yung isa dyan sa typographical errors niya. So, ewan ko kung mali pa rin siya sa 9th edition, but it should be this C5T to the 4th. So, C5 is actually 9.3701 times 10 to the negative 6, and then we multiply this with the average temperature. So, okay. And then, of course, kung ito kasi is actually ginagawa natin siya kasi nga we make sure na accurate tayo sa solution. For simplified calculations kasi, ang ibang gagawin dyan is i-cancel out lang nila itong 5, and then yung specific heat capacity, just to assume na same lang kasi yung ating specific capacity. But for this calculation, gagawin natin is magiging most accurate kung possible naman na maging ganun, diba? So that's it for our specific capacity in terms of joule per mole Kelvin. So joule per kilomole Kelvin. So knowing that this is in joule per kilomole Kelvin, the CPL here, so just to be consistent with this joule per kilogram Kelvin, what I will be doing here is I will be multiplying this with 1 mole or 1 kilomole divided by 18 kilograms, just to convert that to in terms of joule per kilogram Kelvin. So I just have to copy this expression, and then I'll be multiplying this all to 1 over 18. So in that way, I will have this unit in terms of joule per kilogram Kelvin that is consistent with this one. Okay, so now we can plug in this expression, the CPL, in this portion, and then TCO, just let this as X corresponding to this TCO as well. So in that way, we can solve for TCO. So you can just do that on your calculator, and I'll be doing that on mine. Okay, so solving for that, what we get is 343. Oops. So that's 343.22955 Kelvin, which is equivalent to 70.07955. So degrees Celsius. So this is our cold outlet fluid na mas mataas siya sa, of course, sa inlet. So kung mapapansin nyo, this is quite close with 70, which is the outlet hot temperature. Kasi nga, assuming na magkalapit yung ating CP dito and then yung CP natin here. So, practically, it will give us a value that's closer to 70. So, if you would just cancel this out, 70 and 5, and as well as the CP, then you would get 70, which is malapit naman siya dito. But yun nga, sabi ko nga, I wanted to be as accurate as possible. So for asking for the average specific heat capacity for this cold fluid, you can obtain that by the same formula. So what we'll get there is 4,183.9926 joule per kilogram Kelvin. So in this case, we don't break any rule with being consistent with all the average or the bulk temperature that we need to use using this kind of equation. So with that, knowing all our temperature profile for this case, so we know that TCO is equal to 70.07, you can just use 0800 because that's 0.07955. Okay, so now we can now solve for FT by using our effectiveness and capacity ratio. So to be able to get our capacity ratio, it says here that we just need to take the hot fluid on the inside, or the inside of fluid, and then the outside, and then we get the TCI and then the TCO. So actually it should be TCO minus TCI just to make it positive. So going back with this, we can see that that's 90 and then 70, and then we get 50 and then 70.0800. So we get 90 for this one, and then we have 70 degrees Celsius for the hot outlet, and then the inlet here would be outlet will be 70.0800, and then for this one we have that's 50 degrees Celsius. So this is equivalent to 0.996 or approximately equal to 1, but we'll just be using 0.9960 for this one. And kung ang solution niya is cancel out nyo tong CP, then you'll get R equals 1 for this case. And then for S, that's the effectivity ratio, and that is simply equal to the minimum sensible heat over the maximum temperature difference. So we can say that the minimum sensible heat comes from the changes in our hot fluid right here, because that's around 20. For this one, it's just 70.08, so it gives us around 20.08. So let's just use the minimum sensible heat change, and then for this one we get the maximum T difference. So in this case we have 90 degrees Celsius minus 70 degrees Celsius, but it is to be expected that it should occur at the lower profile of the temperatures. But since nga sinolve natin, and then mas nag-increase pa sa dun sa lowest temperature that this profile can get, then we stick with the rule. So that's 90 degrees Celsius minus 70, and then for the max T difference, so basically the maximum temperature difference is the inlet temperature of the hot fluid, this one, and then the outlet, the inlet temperature of the colder fluid. So that's 90 minus 50. So 90 and then minus 50. So this gives us a value of the effectivity, which is 0.5. Okay, so the effectiveness, sorry, I said effectivity. So we have the capacity ratio R, that's 0.9960, and then the effectiveness, that's 0.5. Now we go back with our table right at figure, I think it's figure 11-4. So we check on this, and hopefully we could find FT. So we go back to letter D, and then remember S is actually equal to 0.5 and R is around 1 or 0.99. So this is the value of R. So this is around 1. So basically 0.99 is around very close to this value of 1. And then S is 0.5, so we get 0.5 and then 1. So you trace 0.5 from here, divide it, this is 1, and then you trace 0.5 up to the portion. So as you can see here, our FT is very close to 1. So ito yun. So you start with 1, and then you trace it until you get 0.5. So just take on the intersection of that line. So basically ito yun. So we can just assume na that's 0.99. So our FT would be equal to 0.99. So that's a graphical solution as always. And as you can see here, kapag medyo malabo-labo yung mata, edi mali yung mga uha. Okay, and that's a perspective solution, diba? So I think in a solution, I will be allowing at least something like 0.98 or 0.99 in such case, kasi iba-iba kasi yung pwede natin maging sagot for dun sa gantong medyo malapit na sa top. But it shouldn't be 1. Okay, so in this case, let's plug into that dun sa ating equation para makuha na natin yung kailangan dito. And the thing that we need here is actually the total area of the heat exchanger. So knowing that Q is equal to UA total, and then we get the TM, and wherein our TM is actually equal to the correction factor times the log mean temperature difference. So we can solve for our area total right here. So Q, we can obtain Q from this portion here, and continue pa siya na solve. Q is actually equal to 42,000, 420,000, that's 063.42. So the unit is in MKS. So yun, so just to give you the unit, let's make it watts na lang para may unit tayo. And then yung ating Q, so that is equal to U. Ang U natin from the problem is equal to 800 watts per meter squared. So we have 800 watts per meter squared degrees Celsius. And then yun nga, again, I would like to say na itong Q nakuha natin hindi sa problem, kundi nakuha natin siya dito sa ating Q balance nito. And by the way, kahit gamitin nyo itong 343 for the colder region of the fluid, you will still get the same answer. That's 420,063.42 watts. Okay, so we need the total area right here. So that's 80. And then our FT is 0.99. So that's the correction factor. And then the log mean temperature difference will come from the countercurrent flow that you can see right here on the Paris Handbook, kasi this is the hot fluid and then this is the cold fluid. Because you can see here, it's countercurrent flow. So I'll be using that LMTD for countercurrent. So in this case, we have the temperature difference for countercurrent again. So that is THI minus TCO minus THO minus TCI. And then that's ln of THI minus TCO divided by THO minus TCI. Okay. So in this case, I have the inlet temperature, which is 90, and then minus 70, and then minus, we get THO, that's I think that's 70 again, and then we have here the inlet temperature, which is actually the outlet temperature is not 70 but 70 point something. So that's 70 point 0800, and then THO would be 70 and then minus 50. Then we have ln of 90 minus 70.0800 divided by 70 minus 50. Okay, so if you solve for this LMTD, you'll be able to get a very low value that's around 1.9. So I'll be using a green color for this. That's 1.9. Let me just check it again. So that's 1.959. So when you're obtaining such values na very close to a very small, so there is an error on using this LMTD, because basically yung LMTD should be close to the difference in any of sensible heat that you consider. For example, 90 minus 70 is 20. So LMTD should lie close to those values, as for this example. In our previous example, as you can see here, we have 90 and then 60, so that's 30. So basically the LMTD is 44, and in the same way that's for 60 and for 50 and 10, so that's 40. So basically dun dapat malapit yung ating answers, but as you can see here, we have 20, and then yung sagot natin dito is for LMTD is 1.9597. So why is that? So it simply means that our CP is very close to each other, and in that case our LMTD must be reduced to, this LMTD should be reduced to our THO minus TCI instead. And in any case where you'll be using this THO and then TCI, that should also be equal to THI and then minus TCO. So that would just be the same thing. Kasi nga, basically, magzi-0 over 0 yung ating sagot, which is not actually defined in our equation. And in your module, I also have stated right here that we have here a very important case wherein, in cases of countercurrent, the temperature difference is the same at all locations, wherein the log mean temperature difference is 0 over 0 form, and so we have to use LMTD is equal to the hot inlet and then the cold outlet constant all along. So in this case, so that will be our LMTD, and it simplifies our computation for our LMTD. And as you can see here, this FT would have been easier if we used 1 right here, and then we just cancel out this CP right here. But just to give you an idea of how it works, I wanted you to be stick with the rules na average or bulk temperature ating laging gagamitin, kasi CP is dependent on temperature and it shouldn't be confused with the values right here. Pero yun nga, for simplified solutions, kakancel na nila ito just to give you an idea of how LMTD na 0 over 0 works. So in that way, we write this LMTD in terms of THI and then TCO lang. So this narrows down to 90 degrees Celsius minus 70 degrees or 70.0800 degrees Celsius. This one should be almost equal. Kung cases naman na specific capacity is the same. It's just that hindi siya nagkaparehas dito, so we have to use the one at specified in your module. So in that way, we can now solve for our the correct value for our AP, or the total area. So the total area, so this area is actually referring to all the shell and tube heat exchanger area. Kaya medyo mas malaki siya compared to one shell. So that's 26.6257 meters squared. So if you're asked what is the area of a one shell, so it's just divide nyo lang siya sa 4 kasi meron tayong 4 shells right here. So, yun yung kanya maging area. That's divided by 4 for 1. And yun nga, so dito sa problem na to, medyo marami tayong naging um, conditions na kinonsider. First off is that CP is not CP is not given for the second fluid, and hindi natin inassume na equal yung CP nila provided na magkaiba kasi yung temperature average nila. But if we did, then this will simplify to a very short equation na kakancel mo yung CP as well as 5. Matitira sa'yo is 90 minus 70 equal to TCO minus 50, which gives you TCO that is equal to 70. Which makes this equal to 1, yung ating R, and then which makes our LMTD simply equal to any temperature difference between these two fluids. That's 90 minus 70 in any case, and then this will be 20. So if that's the solution, I will still accept it, no, provided naman na malapit yung maging sagot. So if we'll do that, so you will be getting 20 for this case, and then that's 20 times 0.99, and then that's 19.8. So 420, 063.42, divide natin siya doon, and then divide by 800. So you'll be getting 26.5192, which is still very close to the answer. So it'll still be correct. I just wanted to show you how this works in terms of values that are really not close with each other. Kasi if this, for example, this TCO is not 70, for example lang, especially kung hindi siya same flow rate, mag-iba talaga yan. So this is the pattern of the solution that you'll be doing, and you'll be able to get LMTD na hindi mababa value. Basta remember, LMTD should be very close to the temperature difference between the sensible heat changes of any of the two. So usually nga parang malapit pa siya sa average ng dalawa, like this one. And kung di mo nakuha yung LMTD na yon, so probably may mali sa solution. And you can also check on this sa LN natin, dun niya siya makikita. Okay, so yun lang for this example. Okay, and of course, don't forget to have a look at the direction of the fluid flow for this para malaman natin kung countercurrent ba siya or co-current. But basically, kung mapansin nyo, the movement of the fluid right here is almost always countercurrent for shell and tube. Kasi nga, basically, opposite lagi yung direction nila. But there are cases in which the movement is cross-flow, and that's a different story for this because we'll be solving for that in other examples.